This grad studies in Colorado, Boulder, and then went to MBA for a postdoc where I met him, and I was, heavily moaning about being, punished by Rashid working on my PhD, and so I know him a long time. And then, he went to MIT as a Chandra fellow, and is now in.
Well, obviously, since you're here, the punishment had its reward. So thanks for spending Monday afternoon with me. I'll tell you about a project that I've been working on for the last 3 years, mostly with my grad student Sam Friedman and Eugene Peraza. Eugene's actually a you know him there, but Sam just recently graduated. And so a lot of this stuff is in his thesis in a paper that will come out on January 10th, and it'll probably be asked for PH sometime this week. So, to take away from the title, it has something to do with curls, okay, and it has something to do with shocks, bubbles, and clusters of galaxies. And the connection will hopefully become clear a little bit later on. So, quick outline. I'll motivate why we think there's multi-phase gas in galaxy clusters, and how the presence of bubbles and relativistic plasma in clusters can affect the thermodynamics and the dynamic evolution of the intergalactic medium. And then I'll go into some details about the specific process that we're considering, which is the Riemann-Einthoven stability, the interface between the two media, and a bunch of stuff that, again, I'll clarify at the top. And at the end of that time, I'll tell a little bit about some recent MHD simulations that haven't been published yet. So, to set the stage, galaxy clusters have had a cooling flow problem for the last 20 years or so. And by that I mean that if you look at the surface brightness of galaxy clusters in X-rays, so the altitude of this surface plot tells you what the intensity is, and there are two groups of clusters. They're normal clusters and so-called cool core clusters, or they used to be called cooling flow clusters. And in those cool core clusters, they're very strongly concentrated towards the centers, at the center of the gravitational potential. The density of those clusters is very high, and the cooling time is much shorter than the Hubble time. And so these clusters should lose significant pressure support in much less than the Hubble time. And as a result, because of this cooling, there must be continuous inflow of mass to resupply thermal pressure in the center of the cluster for quasi-hydrostatic ability. And this flow, because it's as a result of the cooling activity in the cluster, is called the cooling flow. And if you just look at the X-ray emission from these clusters, and estimate the star formation rates and the cooling rates you would need to explain the surface brightness of the centers with a simple cooling flow picture, you would find that these clusters would cool about a few hundred to a few thousand solar masses per year. And that's a massive cooling rate. And when people looked to find the star formation according to the cooling rates that were inferred in these very spiked surface brightness profiles, they did not find the star formation. The question was, what happens to the cool gas? Now this first cooling flow problem was replaced with the second cooling flow problem that became clear when Chandra and XMM were launched and looked in detail at high resolution at the spectra emitted by essentially clusters, cooling flow, cool core clusters. And what the instruments found was that the gas cools, as you would expect, because there's a lot of emission. That means a lot of radiation, means a lot of cooling. But it stops cooling about a third of the zero temperature of the cluster. And so there's a temperature floor imposed by something that stops the gas cooling at that temperature, and that's a temperature where the cooling curve actually rapidly goes up, and where you would expect cooling to be particularly efficient. And so you see the difference between the data, which is the black points here, with a good thermal plasma model overplotted, the red line over here, and the actual cooling flow model, the emission you get, thermal emission you would get from a cooling flow at the same cooling rate and dot you get from this. And there's all this flux that you're missing at lines from low temperature species. So something keeps these low temperature ions from forming. Right? Something keeps the gas hot enough to not emit. And so something must counteract the cooling. And as early as 1990, it was realized that a potential source of heat for galaxy clusters are active galactic nuclei, in particular jets at the centers, radio-loud AGN at the centers of clusters. And so ever since, people have tried to understand what the heat source for galaxy clusters is. And should be a picture. There it is. And the first slide I showed you about Chandra XNM was one of the core legacies of the Chandra XNM. A second was the discovery that virtually every cool core cluster, every cluster that has one of these bright centers that should be cooling rapidly, also has active radio galaxies and what we call X-ray cavities in the center. So here is a superposition of X-rays, which is the blue haze over here, non-thermal superconducting radio emission, which is this sort of pinkish stuff over here, and then an optical image of the Perseus cluster where it measures to see where the stars are, where the star formation is. And there is some star formation. A lot of it, as you see over here, this blue light over here, coincides with dark X-ray region. That's a foreground galaxy. Right? So this is the foreground galaxy falling into the Perseus cluster. This has nothing to do with what I'm going to talk about. This is a real X-ray as you would get it at the doctor. Right? So a doctor would shine X-rays at you and look for absorption. This is an X-ray of the foreground galaxy. But what I'm interested in are these regions over here where there's a lot of radio emission, synchrotron emission, from what we call radial lobes from active galactic nuclei. And superimposed, as you see in the X-rays, there's a dark region over here where the radio is. So the X-rays are dark in the centers of clusters. They're what looks like cavities, and overlaid co-spatially is a lot of radio emission. Now, this radio emission was produced by relativistic electrons, the synchrotron emission, and the relativistic electrons and magnetic fields that produce the radio emission were released by a jet from the massive black hole at the center of this cluster. CITA. Now, Chandra finds lots of cavities in clusters. So here is another view of the same cluster, the Perseus cluster, highlighting the presence of these dark regions in the center. These are real X-ray data, and you see that there's a strong X-ray depression in the center. So there's a lack of X-ray emitting gas. That means that there's a hole. And when you overlay the radio emission, it perfectly fills this hole over here. So the X-ray emission in clusters is produced by thermal gas. Clusters are full of hot gas, 10 million degrees, 50 million degrees Kelvin, and densities of something like 0.01 in the centers, and so that emits a lot of X-rays. 90% of the baryons in clusters are in this hot gas. And so that gives you the X-ray emission, and the fact that you don't see any X-ray emission over here means that there is no thermal gas in these bubbles, in these cavities. Instead, you see radiation. So there's relativistic gas, relativistic electrons in the magnetic field that fill these cavities over here. So this is one of the core legacies of the Chandra telescope in cluster science. The next one was the fact that we actually, when we look at some clusters, we actually see not just cavities, but we also see shock. Now this doesn't come out particularly well here in this image, partly for contrast regions, but there is a shock. Oh, thank you. You can turn that back on in a second. So there is a surface brightness discontinuity over here. Sort of extends all the way around. There's a shock front. You can measure the pressure jump across this front over here, and it's clearly a shock. It's a weak shock. It's about Mach 1.4, but it's definitely a shock front. So Chandra is critical to finding these because of the high spatial resolution. So we found numerous shocks, weak shocks in the centers of clusters. And then, in addition, Chandra also found a series of sound waves, or weak shocks, that emanate from the center. This is, again, the Perseus cluster. And now what you see here is an unsharp masked image of the X-ray emission. Yeah, unsharp masking brings out contrast in images. You can use it in Photoshop to increase the contrast of the image and to heighten edges. And this is a technique more and more used in X-ray astronomy these days. And you see these ripples that sort of are concentric around the nucleus of the cluster, which is right here. And so these have been interpreted as nonlinear sound waves that have been excited by the activity of the AGN in the center. And so you can measure the wavelength and you can estimate the frequency. So these sound waves have a frequency of 10 to the minus 4 BPM, where m is beats per millennium. Okay? So these are very low frequency sound waves. And so they propagate through the cluster. And you can actually count the amount of energy, and some of the amount of energy transported by these waves, and it is significant. Now, why do I care about the energy? If you remember, I said clusters require some kind of energy input. Right? They need something that keeps the gas and clusters from cooling. And since I said AGN are a prime target for this heating activity, we have to understand where the energy from an AGN actually goes. Right? So we understand that it inflates a bubble. Okay? So if you inflate a bubble, right, so you blow up a balloon, what happens? Well, some of the energy goes into internal energy of the balloon. Right? That depends on what the state of the gas is inside. Now, for non-relativistic monatomic ideal gas, the amount of energy per particle is 3.5 kT. Right? And so what you need in terms of energy is 3.5 PV, right? To just account for the internal energy of the bubble. For a relativistic gas, the amount of internal energy is 3 kT, so 3 times PV. And so relativistic bubbles contain more internal energy. The rest of the energy goes into PdV work on the environment. So that's roughly of order PV. Right? Another factor of PV, basically the integral of PdV, goes into the environment, and a lot of that energy goes into these waves. Right? And sound waves, even if they're nonlinear, are very weakly dissipative. So they take a lot of their energy with them. Right? And sound waves travel at the sound speed, and where do they go? Well, they travel out away from the center of the cluster and take all that energy that you want to use to heat your cluster with them. Right? That's not a very efficient way of heating a cluster. Sound waves are not a good way. And weak shock waves are also not a very good way of heating clusters. If you want to heat your cluster well, you have to produce a strong shock wave. You have yet to find a cluster that makes a strong shock wave. You have yet to find an AGN that does that. So the question is, can we tap into this energy that goes into the wave field and use it to heat the cluster? So that was the motivation behind the talk, behind these discoveries. So this is the Perseus cluster. Okay. So here, just to show you how much energy is actually inflated, it's used by the AGN to inflate these cavities. Here is again an image of the Perseus cluster, and now overlaid the contours of the 1.4 gigahertz radio emission. And you see that it nicely fills these two cavities, right? The color scale is the X-rays. And so the question is, how much energy does it take? Well, as I said, roughly 3 times PV for the internal energy of this bubble, and another factor of PV for the PdV work on the environment, a lot of which goes into these waves. Okay, we can estimate the age by estimating the expansion velocity of the bubble. They're not strongly supersonic, otherwise we'd see a strong shock. Right? So roughly a quarter of the sound speed, which is roughly a quarter of the buoyancy speed. So these are rough estimates. And so the age is just the size of the bubble divided by its expansion velocity. And so now we have energy and age, and that's a pretty simple calculation. Power is just the energy divided by the age. And so in this particular case, the power by the AGN averaged over the inflation history of this cavity about 10 to the 45 joules per second. And that is more than enough in principle to provide the heat to counteract cooling in this cluster. Okay. But a lot of that, as I said, either goes into the internal energy of the relativistic gas, which is not where it needs to be. It needs to be in the internal energy of the thermal gas. And the rest goes into this acoustic field, right? The waves that are excited, that are not strongly dissipated. So here is a plot that shows the cooling power of clusters versus the inferred jet power. It's inferred from looking at these cavities and how much, the same estimate I just showed you, how much energy you get from that. And so this middle line over here shows you where for a particular cluster heating equals cooling, or at least very simple. Energy input by jets into cavities equals cooling. And then you have to transfer that energy to heat. So that's what we're after. And so these clusters straddle that line of heating or energy supply equals cooling. And if we can find a mechanism that is fairly efficient in principle, we can imagine that many clusters can, on average, jump back and forth between heating equals cooling. When a cluster has a stronger cooling activity, right, you would expect that gas collects in the center of the cluster. Right, because it's potential well, cool gas wants to sink to the bottom. What will it find at the bottom of the cluster? Well, it'll find the CD galaxy, and in the center of the CD galaxy is the black hole. If you increase the mass supply of cold gas to the black hole, you will increase the energy output of the black hole, you will increase the energy supply of the cluster. And so you can think of this as sort of a thermal feedback loop back and forth across this line, if this process is efficient enough to actually use the cluster. So this is a negative feedback loop, where if you cool more, you produce more energy output by the AGN. In principle, you can then try to convert that energy to thermal energy in the cluster. Here is another plot that shows the inferred jet power in these clusters compared to the simplest estimate of the accretion rate onto the central black hole based on the properties of the cluster. And again, you see that the two track each other pretty nicely, which is again sort of an indication that the black hole really does accrete from the thermal gas of the cluster, and it does know about the thermal state of the cluster. So this feedback picture seems to hold together, at least from the observational side. So theoretically then, the question is, can we heat clusters by this process? I'll skip the slide. Well, I'll just say that this radial mode, this feedback of jets, radial bubbles inflated by flows from black holes, has also been invoked in the context of galaxy formations, in the sense that you need some kind of energy source to keep red elliptical galaxies from becoming blue again and sort of shutting off star formation. This is a similarity, but the talk today probably is not in direct relation to that particular process. So, as I said before, we have galaxy clusters filled with cavities. Okay? And so that means that we have a multi-phase gas. We have a thermal phase and a relativistic phase, magnetized relativistic phase, strongly magnetized. In fact, the magnetic fields inside these cavities, right, the radio-emitting bubbles, are close to a partition. And so this is quite different thermally and dynamically from the thermal gas in the cluster. So this is one way of thinking of multi-phase gases with bubbles. My former advisor, Mr. Spiegelman, came up with this picture of effervescent heating in galaxy clusters, where it basically postulate that galaxy clusters are filled with relatively small pockets of relativistic plasma. And the observations seem to support that. If you look in very fine detail at the nearest clusters where the resolution of the instruments is high enough, you do see that the structure of the radio plasma of the X-ray gas is very filamentary. And then questions arise such as what happens to a cavity buoyantly sitting in a gravitational field, right? These are relativistic gas cavities, right? Bubbles are relativistic gas at very low density. Relativistic gas, of course, has a lot more pressure per particle, a lot more energy per particle than non-relativistic thermal gas. But these are low density bubbles that are in principle buoyant. And in the process of buoyancy, these bubbles get burst. And there could be mixing and all sorts of interesting things. What I want to focus on for the rest of the day is the question of what happens when you have a spectrum of cavities, right? Bubbles of low density gas, and in the presence of waves, shock waves or nonlinear shock waves, as we see exist in clusters. Both of those exist in clusters, and there are multiple generations of cavities and multiple generations of waves from multiple generations of activity of the nuclear black hole. Both is observed. Here is my sketch, right? So here are the waves and multiple generations of these bubbles in the cluster. What happens when the two interact? To some degree, you cannot avoid the interaction of those two complements of the medium. We know both exist, and these waves must pass the bubbles. The bubbles move much slower than the sound speed, and the waves move at least at the sound speed. The shock waves can move faster. What happens at the interface of those two?
But aren't the bubbles buoyancy not the same speed as the sound speed?
The buoyancy speed is about half the sound speed.
Oh, you're talking about that half.
Yes, at most. Depends on the size of the bubble, right? Smaller bubbles are slower. So that depends on the size of the bubble. So what happens when you have bubbles that interact with something? So here is a computerized version of that interaction. Since we can't observe clusters in real time, at least we can simulate this. So I'll boil this down to a very simple hydrodynamic experiment. So here are a couple of things plotted on this what will become moving in a second. So there's a density contour. This red contour over here is a density surface. And that's the bubble. Right? So inside this bubble is low density gas. But then I plot the pressure and the density contour of high pressure and high density gas. And that's the shock. Right? So the shock gas is on this side, and the unshock gas is on this side. And the shock is going to be moving in this direction. And so the pressure and the density contour are just slightly offset with respect to each other. And then on this face over here, I plot what's called the entropy, which is just the density times the vorticity squared. And it's a poor man's measure of how much energy is in what I call the vortex field. And I'll motivate why I thought this in a second. And then on this space over here, I plot the what we call the baroclinic term. It's the cross product of the gradient of pressure with the gradient of density. Okay. So the important bit to watch is what happens to this cavity. Okay. So who has an idea of what's going to happen to the cavity? It's going to be rolling and blowing. Yeah. So the tidal at the top will all curl up. Okay. So here's what happens. Okay. So the shock passes, and the initial spherical bubble is turned into a vortex ring. Okay. And so this is a well-known process, and it's essentially a macroscopic representation of what's known as the Riemann-Stieltjes instability. Okay. So this is an instability that occurs when you have pressure and density gradients misaligned. That's why this term, the cross product of pressure and density gradient, is important. Whenever this term is non-zero, you create vorticity. And so you can see where the vorticity is generated. And you can also see it in the shock wave over here. Since these are pressure and density surfaces just slightly offset from each other, whenever they cross, so that is whenever you see purple poking through this sort of blue-green surface, that means that you violate the baroclinic condition, where gradient with pressure and density are parallel to each other. And those are the loci, the locations where you generate vorticity. And so you take completely irrotational flow. For action, you generate a strong vortex flow around the location of the flow. So you see this differentially rotating vortex, which is kind of like a smoke ring. Right? So if this would have been 20 years ago, I would have taken a cigarette and blown a smoke ring. But these days, they're really cigarettes, so it's not allowed anymore. And at home in my office, I have a vortex gun, but you can't travel with guns. So the vortex gun is just a little big piece of plastic with a membrane inside. So, but this is what happens. And so this must happen to some degree in galaxy clusters as well, when shock waves pass these filaments of low-density gas. Okay. So this doesn't happen just in galaxy clusters. This actually happens in lab experiments too. So this is a picture of this constant shock tube, which is just a few buildings down from where I sit. It's a nice steel tube, but this big around and 3 stories high. And at the top, they have steel diaphragms about this thick, and they pressurize the cylinder on top, and they blow a fuse basically and crack it. Steel membrane, and then shock goes down. And on the right, this is what they filmed. So this is a slice through basically one of their experiments. And you see this nice. This is now basically projection perpendicular to rotation axis of one of these vortex rings that forms when a shock runs over a spherical bubble. It's quite cute. They have a nice thick glass window at the bottom of this thick, and they have a tiny straw that they insert into this shock tube and inflate a helium bubble just before they set up the shock.
Where is the bubble?
So the bubble is up here, and then the shock pushes it down, and then they track it with the camera. The bubble actually moves with the shock as the shock runs down the tube.
So the growth of the instability is modest compared to the speed of the shock.
Yes. That depends. Yes. So that depends on the shock strength actually. So for weak shocks, it's very slow. For strong shocks, the vortex forms before the shock has actually passed the bubble. Okay. So what are we left with? We have this vortex ring, right? The velocity of this vortex is roughly a quarter of the difference in velocity posed in free shock. Right? The velocity jump across the shock. That's the characteristic velocity of the problem. But it cannot, rotate at this speed out to infinity. The velocity must drop fairly quickly. So we have a differentially rotating flow. But instead of having, a 1D, 2D accretion disk, think of an accretion disk that rotates like this, stretched out into a torus that does this, right? And so in these differentially rotating flows, there are ways, of course, to dissipate the energy that's in the rotation. And so the question then is, how much energy can you extract from this rotating flow before this vortex has traveled away from the cluster and put it back into heat in the cluster? So in order to characterize the amount of energy that ends up in this differentially rotating flow, we do a Helmholtz decomposition of the velocity field to extract only the rotational part of the velocity, only the solenoidal part, the part of the vortex. Right? Remember, there are acoustic waves. Oh, that's not good. So they are acoustic waves. That's the wrong talk. I think my talk is right. Well, let's start this again. Okay, so there's a rotational and a purely acoustic part of the velocity field, and we can deconstruct them, right? Just like you can deconstruct any vector field into a solenoidal part and potential part. And you can write the solenoidal part as the curl of some vector potential, right? And that's what we do. So we have this rotational part of the velocity field, and that is the irreducible energy, eventually, if we add this all up, that is in that vortex field. And that's the free energy you have to dissipate in this process. And so, to solve for the vector potential, which is what we need to get to the velocity, we calculate the vorticity, which is the curl of the velocity field. And that must be the curl of the vector potential. We can solve this equation for A. And once we have A, we can go back to B. Right. Now, you can rewrite this as the sum of these two terms. There's some freedom in choosing A. Right. Just like you calculate the potential for a magnetic field, you have gauge freedom, and so we can pick a gauge where this is 0. The Coulomb gauge basically where this term goes to 0, and all we have to do is solve Poisson's equation, essentially for A. Right? So the vector Poisson's equation. We can calculate this, we can get that, and then once we get that, we can back to the irreducible part of the vortex. So that's the analysis we do in these simulations. The only complication is when you reproduce, or when you write Poisson's equation on a finite grid, this is the standard form of the velocity, right? You take points plus or minus 1 from the grid position, and then you solve this equation, usually spectrally, right? You do a Fourier transform, and then you solve for the components of the Fourier transform. The problem with our simulation is that we're not actually trying to solve for A. What we're really after is this. So we have to do one more curl. So we have to do 2 curls, right? So these 2 curls introduce an extra offset numerically in our finite differencing scheme. And so we have to solve Poisson's equation, what's known as a non-compact stencil. And it's a slightly more complicated procedure. So the details of this are given in Sam Fried's thesis. And so we then use classic FFT to solve. Okay. So here is, as I said, let's just say we have a mixture of hot and cold, non-relativistic, relativistic, and thermal gas. And what happens when a shock runs over a spectrum of bubbles? Well, here is an even simpler simulation, just to highlight what happens in 2D, and the visualization of this deconstruction into this irreducible rotational component of the velocity field that gives you the energy in the vortex field. So you can forget about all the acoustic energy that you accept in this process as well. So there will be a wave that travels from left to right here in this density field. So here it is. It goes to the right, and it turns each of those little bubbles into a little turbulent vortex, basically. So that's what happens in the density. And now on the bottom, I'll show you the solenoidal part of the energy, the acoustic part, and then this clinic term over here, just for reference. So it's a little slower. And so here, this green stuff is all basically the initial wave that passes through this box, right? That's all acoustic, all potential. And you see that there are some waves that are excited, that are reflected basically off the back here. These are all acoustic waves. And the red stuff, the red is the rotational part of the velocity field. And so that is trapped at the location of the initial phase. So it's traveling much more slowly than the shock. This is a weak shock. So this is applicable, principle, of course, it's still a toy simulation, to the intergalactic. So this is what we do, this is what we calculate. We basically sum over the red part of the velocity. We sum over the rotational part of the velocity. And so the question is then, how much energy is left in this differentially rotating vortex ring? Can we use that to heat the cluster? So we filter out the acoustic part of the energy. And then you can easily write down the order of magnitude you would expect for the kind of energy that you get in this vortex, right? It's just a dimensional analysis argument. Well, the integral over the kinetic energy density would just be the volume of the bubble, that's the order of the size scale that we're talking about, times delta V squared, where delta V is the velocity difference across the shock front, the wave front, okay? Divided by 2, of course, and then multiplied by the difference in density inside and outside of the bubble. Right? If they're identical, the density inside and outside of the bubble is identical, you shouldn't get any vortex. You shouldn't get any vortex, because it looks the same, right? There is no density gradient to generate vorticity. And then there is some correction factor, right? This is just the dimensional estimate, and there's some correction factor that we want to calibrate numerically. Right? And so you can call that basically a vortex string, sort of, like an oscillator string. So this is essentially the efficiency coefficient that tells you how much energy actually goes into this vortex. So this is the setup here is the shock gas, it's the velocity jump across that shock. This is frame 2, this is frame 1. And so I will plot essentially the results for this calibration factor, right, this efficiency factor, to show you how efficient this process actually is. And a good efficient process would get something of G of the order of unity. Right? That's about as much energy as you can hope to get from the process. So here is a resolution study that shows you the result for one of these G factors. Now measured in the downstream, you can measure them upstream, it doesn't really matter. The only difference is that there's a density factor which changes as you cross the shock. And so this is a function of time, and you notice as the wave crosses the bubble, the amount of energy in the rotational field rises and then plateaus. Right? And so this is for low resolution, higher resolution. Eventually, when we reach about 100 resolution elements across the bubble, we converge. So the simulations are converged, and we can now calibrate this G factor as a function of, for example, Mach number. So here I plot G2 as a function of Mach number of the wave. So shock wave. Very weak shock, very strong shock. Now, for very strong shocks, I'll show you in a second, the shock, or the curve actually never really plateaus. It decays very quickly. And the reason for that, I'll get to in a second. So these are really only the maxima of this curve. Whereas over here, those curves plateau. You can really define, you can well define that efficiency factor. And so for the two-dimensional simulations we did first, this factor is about unity. So it's just about as much energy as you would expect from the dimensional argument. Right? And if you go to 3D, the efficiency jumps by a factor of 2. Right? And the reason for that is that in 2D, a bubble is really a cylinder. Right? It's just a plain parallel simulation, and so a bubble is really a cylinder. And I told you before that vorticity is generated when the pressure gradient and the density gradient are misaligned. Now this is the shock, right? The pressure gradient is perpendicular to this direction. Right? This is the pressure gradient. This is the bubble. Right? At the head of the bubble, the density gradient is in the same direction as the shock. Right? So there's no vorticity generated. The maximum amount of vorticity generation is at the equator of the bubble. Right? The density gradient is in this direction, pressure gradient is in this direction. And if you have a cylinder, there's a lot less area where the two are perpendicular than if you have a bubble. Right? With a bubble, anywhere around the equator you have this. So that's why 3D is about a factor of 2 more efficient. So this is one of the takeaway points. This instability is quite efficient at generating energy in this vortex field. Okay. So what happens if you have multiple bubbles? What I showed you before was a hydrogen simulation of just one bubble. Right? And the results of these hydrogen simulations were different Mach numbers. What happens if you have multiple bubbles? Well, the two can interact. And the vortices can actually affect each other. Right? So this is before and after. And these are not exactly perfectly round donuts anymore. Right? So you notice that the multiple bubbles can significantly affect the evolution of their vorticity respectively. And so here are a couple of test simulations to evaluate roughly what happens when you have densely packed bubbles. And that depends a little bit on the geometry. So if you have two balls that are aligned like this, you actually increase the amount of energy that's extracted. And that kind of makes sense because now you have, it's almost like an extracted bubble. It has more surface area where the density gradient is perpendicular to Whereas if you have them slightly offset, once they start interacting, the energy actually goes down. And when they're far enough apart, roughly about 4 bubble radii, nothing much happens, right? This is roughly the same you would get for a single bubble. In units of the efficiency of a single bubble. Okay, so as I said, we would expect a spectrum of cavities in the clusters, so this must have some effect on the efficiency of the process. Okay, so can we observe some of this? So as I said before, I'll get back to the heating. This must happen to some degree. Can we observe it? So here are some virtual Chandra observations, and most importantly, here the virtual radial map of the synchrotron emission you get from a bubble after it's been hit. So this is at different viewing angles, face on to edge on. And so you see this nice torus ring that you'd expect from one of these vortices. So here is a radial map of the Virgo cluster. There's multiple sort of generations of filamentary radial cluster, but there's this very nice ring over here that has been dubbed the radial ear of Virgo. And when you look in the X-rays, there's a shock that sits about right here. So it has just passed this region, this bit over here. So this is the shock over here. Not so clear to see, obviously. This is the X-ray. So there's a shock over here. There's another shock over here. And this, at least today, to me, is the best example of something where this might have actually happened recently. You can actually observe it. But it's basically the nearest cluster that we have at our disposal, and it's going to be hard to find this in other clusters. Nonetheless, I've just come back from the VLA last week, and the increased sensitivity of the EVLA allows studies of clusters in much more depth and much wider fields of view, and there are a couple of clusters they showed me that had really looked like nice rings of radio emission. So this is promising. Okay, so that's the imaging signature. Can we observe this spectrally as well? So these are emission line spectra, basically, where a delta function emission line calculated through our simulation box at different viewing angles. So this would be viewing edge on, so the vortex ring is in this direction. And this is face on. The vortex ring, from your point of view, looks like this. And so this is what the velocity profile of this vortex ring does to a delta function. It smears out a delta function in this line profile over here. And so this is for different time steps of one simulation. And they basically look very, very similar to each other. Right? So there is what looks like, at least for this particular Mach number, a universal line profile you expect from this vortex ring that you get from shock bubble interaction. So you take a delta function and you smear it out into this line profile, and the line profile has a dependence of something like delta Newton minus 2 at the core. And then there's a cutoff over here at the edges of the line, because as I said, the characteristic velocity of the problem is delta V across the shock. You cannot generate velocities in the thermal material that are much larger than that. So that's the characteristic velocity. So observing something like this will allow you, A, to measure the characteristic velocity, and B, to infer the presence of the vorticity field. You can do this for different Mach numbers as well. Right? So this is now for Mach numbers from, I believe, 4 to 1.5 down to 1.08. And so this is the line profile function you get for each of these different shock strings running over a spherical bubble. This is edge on again, so the vortex donut ring is perpendicular to the line of sight. And they're self-similar, except, of course, to this cutoff, which moves in for higher Mach numbers. This is with respect to the width you would get for that shock. Right? So this Newton minus 2 profile seems to be a universal profile for vortex field generated in a shock bubble interaction. And you can understand that as an expression of the velocity field by looking at the velocity field. Now, this is for edge on, and you get differences in the wings of these lines. So in the core, they still follow this nice delta profile. So this is going to be tricky to observe. For one reason, lines have thermal broadening, of course, and thermal broadening competes with the simple velocity broadening you get from this process. And you'd have to look at significantly massive species to see this effect. So iron, would be the best hope in collecting the agent. So being a fairly abundant species, it's heavy enough that the thermal volume could be small. So this is a velocity field. So the streamline is basically, and then the length of the arrow tells you what the velocity is, the magnitude of velocity, around one of these vortex rings. So this is a cut through the simulation. And so you notice that fastest velocity after the spine, and then as you go away from this vortex, velocity drops. And you can show that this delta Newton minus 2 profile is a result of a velocity profile that goes like r minus 3, the distance from the center of the vortex. Right? So this is a plot of the velocity, the rotational velocity is a function of distance from the center from the axis of the vortex. And it definitely has an r minus 3 profile that's plotted over here, r minus 3. And these are velocity contours that also roughly follow this. The ring, the gray stuff is an r minus 3 profile, and the red is velocity profile, the actual velocity profile from this simulation. So if you convolve this, through the line of sight, you can actually get delta Newton minus 2. So this is a prediction that hopefully, maybe with the launch of Astra H, which has colorimeters, it's an X-ray mission with high resolution spectroscopy on board, will in principle be able to observe. Unfortunately, Astra H doesn't have particularly good, doesn't have any spectral resolution really, so you can't really make images, which would be nice. Since IXO was recently killed, we don't really have any hope of doing this with imaging in the future. Okay. So,
question.
Yeah.
Easier given the force of the defenses of wrap up in the field.
Yes. So
brightness fluctuations and so on.
So that's something that that's a good point. Unfortunately, my clock here reset, so I don't know how much time I have left. If I speed up a little bit, I can show at least what this looks like with MHD. Okay. Okay. All right. So vortex stability. So as I said, this is a differentially rotating vortex, right? And velocity goes down as 1 over r cubed. Now, it's long been known that differentially rotating vortex flows can be unstable. Right? So these are two rotating cylinders with different rotation rates, an inner and outer cylinder with fluid interface, at different Reynolds numbers. All right? And at low Reynolds numbers, the flow is laminar and stable. And if you increase the Reynolds number, this flow becomes unstable to the classic Taylor-Britten stability. Okay. And so this is an experiment. This is a computation that shows the development of these rolling eddies for larger Reynolds numbers. And differentially rotating flows are classically stable if the Rayleigh criterion, which T here, is satisfied. So if this derivative of the differential rotation velocity with respect to radius is larger than 0. But these flows go like v proportional to r minus 3. So r, they are with like r minus 2. And it's definitely negative, and so these should be unstable. So the question is, how unstable are they? And the onset of Taylor-Britten stability is governed by this Taylor number, which is essentially the Reynolds number squared. So this is the difference of the two cylinder. In this case, we have a cylinder that's far, far away, but the velocity drops very quickly. And so we can replace this delta r just by the size of the radius of the vortex length velocity to get the order of magnitude. This is the viscosity, and this is the frequency. So in our case, this is a very large number. Fairly large number. Now, the Taylor-Britten stability is something that has been studied for cylinders, and it's hard enough to do the analysis in the cylindrical case. Now, in the case of a differentially rotating vortex, think of a cylinder as being bent like that. Right? So it's a Taylor-Britten cylinder bent to make a donut. Right? And so instead of having the waves behave like that and get the rolling eddies like that, the waves should go like that. Okay? And in fact, when we look at the late stages of some of our simulations, they actually do develop these large-scale eddies that are about the right wavelength. And so the Taylor number of the simulation, the highest resolution simulation is something like 10 to the 7, and they should definitely be unstable. Okay. So the Taylor number actually does depend on the Mach number of the shock. And so high Mach number shocks tend to be more unstable. And here's a Mach 8 simulation of a spherical bubble, and this doesn't look much like a vortex rotating bubble. Right? So after a few rotation times, the high Mach number simulation is actually completely disintegrated into a turbulent field. And once it looks like this, it dissipates numerically very quickly. Right? Numerical viscosity will quickly dissipate this voltage over here. Which is why, as I showed you before, for high Mach numbers, the efficiency peaks and then drops very quickly because of this dissipation. Okay, so speaking of dissipation, even if there is no turbulent dissipation, even if the vortex rings are stable enough, you can still dissipate the energy viscously, just like you do in accretion disks, whatever your source of viscosity is. And so you can write down what the viscous dissipation rate is. Okay, well, all you're really doing in this case is taking the equations and making a dimensional analysis, and then numerically calculating post-processing in our simulations an efficiency of viscous dissipation. Now I should say that the simulations were implicit in the sense that they didn't have any extra viscosity in addition to numerical viscosity, which of course is artificial. But we can still calculate in post-processing just from the calculated velocity field what the viscous dissipation rate should be. So the viscous dissipation rate should just be the order of the bubble volume again, times essentially the velocity gradients squared times the viscosity. The viscosity factor here. And you can characterize the viscosity in terms of the Spitzer viscosity, the Spitzer-Rensky viscosity, which is just microscopic viscosity. With some efficiency factor. So we have two efficiency factors. This we can evaluate numerically. This you have to assume some factor for, depending on what fraction you think the actual microscopic viscosity has of the microscopic Spitzer viscosity, which is the maximum value you would expect without any magnetic field. Magnetic fields, of course, suppress viscosity because particles are trapped under our orbits of magnetic field lines. And in principle, it's been speculated that this factor could be fairly small. Anyway, so we have these factors, and we can calculate the viscous dissipation rate in post-processing. And then we can get from that the dissipation time. Right? And this dissipation time is listed in units of this dimensionless number over here. Right? So from that plot, we can actually infer what this number is over here. And this number is about a factor of 10, which suppresses, or which reduces the dissipation time by a factor of 10. So viscous dissipation is fairly efficient. Of course, it depends on the microscopic viscosity coefficient, right? But at least this sort of macroscopic efficiency coefficient, which is a function of the velocity profile and the density distribution of our simulations is fairly high.
So higher than the numerical version of it?
Yes. Well, that of course depends on the Spitzer viscosity, right? Yeah. So and what factor?
So with your assumption, you should probably be moving in the direction of the simulation.
We should, if it's large, right? But we don't know what the value is, right? So I mean, we left it out because for the calculation we're doing it's not necessary. And of course, if you really want to calculate what the long-term evolution is, then you should include it. And that, in fact, will of course also affect the stability of the vortex because the more viscous it is, the more laminar it becomes, the less unstable it becomes. So you can basically write down conditions under which the viscous dissipation is sufficient to dissipate the energy of the vortex before the vortex is completely combusted. So conditions under which heating might work, so under which you can actually transfer this energy from the vortex into the thermal gas, which is what you want after all. Right? We want to take energy from the wave field, put it into the vortex, and then dissipate it. This works if this combination of dimensionless factors here is smaller than this. Right? So for fiducial numbers, bubble scales of per parsec, typical densities, cooling function of 10 to the minus 23, which is typical for these temperatures, and Spitzer viscosity of order unity, and typical cluster temperatures, this is an order unity. Right? So as long as this is smaller than that, you're plenty viscous to dissipate that vortex before the cluster has time to cool. Right? But of course, if you increase the size of your bubbles, or if you decrease the efficiency with which you dissipate, decrease your viscosity, then this number goes down and becomes harder. So it's possible, though, for reasonable values of cluster parameters, that dissipation can be efficient. So that's one condition. And the viscous dissipation time also has to be short compared to the residence time of that vortex in the cluster. So the vortex still travels. is just traveling slower than the wave that excited it. Right? So if the vortex takes its energy out of the cluster before it dissipates, then you've still lost the energy. And so another set of dimensionless numbers, right? And again, for fiducial values, this is order unity, and as long as this is smaller than 150, you're good. Right? But again, this depends on the Spitzer factor here and the size of the bubbles. And again, for large bubbles or weak viscosity, this could become a problem. So you're still, it's unclear exactly what the best values are to plug in. You don't know what the viscosity is. We can measure the largest scales of the bubbles, but there's a spectrum of bubbles, so we don't really know what the best values are. So there's a range of values that work. And then finally, you have to have enough bubbles to make a difference, right? If you only have one bubble in the cluster, most of the shocks will never see that bubble. Right? They will travel in a direction different from where the bubble is. And so you have to have a large enough filling factor. It turns out that filling factors of a few percent will be enough to dissipate sufficient energy. So this again depends on the wavelength of the shock, or the sound waves, and the size of the cooling region of the bubble. So a few percent. So those are the three conditions. And there is a region of parameter space where they can be satisfied. Okay. So last minute, the question came up: what happens when you add magnetic fields? It's always a good question. The simulations I showed you were hybrid. Here's a sketch of 2D simulation that we've run to show what the different setups are. You can, this is again an infinite cylinder. I'll show you 3D too, so there'll be two of that. Just to demonstrate it. So there are two different orientations of the magnetic field, perpendicular and parallel to the shock front, and they have very different outcomes. In the perpendicular shock, which is this, you can still make a nice vortex. It's a little flattened, right? But you can still do it. In the parallel shock, you definitely have a much harder time of exciting the explosion. Here's the same thing in 3D, but what I'm actually plotting here is the rotational energy, the energy in the vortex field. Right? Before, the energy was in this nice vortex that was rotating where the bubble was. Now we have this particular simulation, the bubble, the shock runs in this direction, and the magnetic field threads the bubble like this. And then what you see is that the energy in the vortex is not trapped where the bubble is, but it travels along the magnetic field, essentially as a torsional plane wave away from the bubble. It transports some of the energy. And so this is another way of putting energy directly from the bubble into the cluster. This might be a very nice way of distributing the energy in the cluster rather than moving it away from the cluster.
What beta are you using for the background?
So this is the beta is, I think in this particular simulation, 10. But this is not a particularly realistic scenario for the magnetic field configuration because the bubbles in clusters, remember these are AGN-inflated relativistic plasma bubbles, look like they're magnetically confined, and it looks like they're magnetically isolated, right? It's hard to imagine that you inflate a bubble from the jet of a black hole that sits nicely like a bead on a magnetic field that threads the cluster. So what's probably more realistic is a simulation like this, where you have a magnetically isolated bubble. I don't have the simulation for this. I don't have a movie for this, unfortunately. But yeah, we're working on that. So this is the initial stage. This is the shock, or a density jump over here. The shock travels in this direction. And the field is tangled inside the bubble initially. And once the shock is passed, it twists it nicely into this, what looks like a donut. And this is where you would look for the signature, presumably in synchrotron emission, from the particles. And so this is probably what the ring looks like that I showed you for M87. Right? So with polarization information, which the EVLA will hopefully provide, we can then try to disentangle whether this ring, radio ear, in Virgo is actually something like this. And so last slide is just, again, this efficiency factor that shows how much energy goes into the vortex as a function of time. And so this is the weak field case, which is essentially identical to the hybrid case. It's a beta of 100, right? And so this is the ratio of particle pressure to magnetic pressure. And so this is a case where the magnetic fields are weak and they're dynamically unimportant. So it's very little suppression from the hydro case. And if you increase the magnetic field all the way up to excitation, you can reduce the efficiency of vortex creation just by magnetic tension, basically, which resists this twisting by a factor of maybe 30%. But it's not particularly dramatic. So the presence of magnetic fields themselves really does not affect the development of stability particularly. Okay, so I'll put my summary up, since I'm already 5 minutes late. I'll just leave with that questions.
Yeah, so maybe we have time for one more question.
So the damage effect could suppress the field compress quit
It could. I mean, we haven't actually investigated that part. I mean, so it does not suppress the Riemann-Dimensional stability, which gives rise to the vortex. Now, if you, it does suppress it strongly if you thread the bubble on a homogeneous magnetic field, right? Because then you have a lot of stress that's provided by the field that's anchored in the thermal gas. If the field is inside the bubble and is magnetically isolated, the suppression is fairly weak. If you suspend the bubble on large-scale homogeneous field, you can suppress the efficiency by a factor of 10. Right? So we did calculations where we calculate what the efficiency is for beta of 1 in this homogeneous case, and it's down by a factor of 10, as you would expect. But in the tangled case where the field is isolated, the effect is fairly weak. How it affects the onset of tail stability, I don't know. It's a good question. We'll have to have some higher resolution simulations for that. Because you have to have high Reynolds numbers to really see this. And the 3D MHD runs are a little bit more expensive than the hydro runs. And so we haven't really got to that resolution like that.
So, I mean, maybe you mentioned this already, but what's the lifetime of these smoke rings?
Well, so this depends on the viscous dissipation time and the turbulent dissipation time. And so for high Mach numbers, the turbulent dissipation time is only a few indeterminate times. And so they will probably disintegrate fairly quickly. On the other hand, we don't really see any Mach 8 shocks in clusters. So that's probably not that relevant. And we don't know what the viscous dissipation time is, because we don't know what the viscosity is. So hopefully short enough that it dissipates much of its energy before it leaves the cluster. In terms of physical timescales, that depends again on the size of the bubble. Smaller bubbles are easier to dissipate. So maybe tens of millions of years for a kiloparsec scale bubble. And a few hundred million years for 30 kiloparsec scale bubble, which is the upper end of what people observe.
So you won't see that many like this.
Well, the small ones are going to be very hard to see because you need the high resolution X-rays and you need a lot of photons. And Chandra is high resolution, but not a lot of photons because it's not a big instrument. And yes, we don't really know. And we know that there's a lot of radio flooding. Like there's a lot of synchrotron emission from clusters. And there are halos, cluster halos. There are relics in clusters, and there are so-called mini halos. These are all synchrotron sources of emission. And it's not clear on small scales what the structure of this plasma is. Right? It's probably not volume flowing, so there are filaments with relativistic plasma in clusters. But what the scale of the filaments are is not known.
Okay, maybe we take Sebastian out for cookies. So let's thank him again.